Physics students. So I want to spend a little bit of time going over the test, and all in all it went well. Your scores have been input. Here's the question that kind of was missed quite a bit. It was that question number 6, is you had this setup and you had the YouTube literally, and you had oil here, and then you had water here, okay? And you're told that this was 27.2 centimeters. Then you're told that this was 10.2 centimeters, okay? So here's the whole idea of this, is that at any depth, okay, like if you go across here, these pressures have to be the same. So if you look at P naught plus rho GH on the oil side is going to equal P naught plus rho GH on the water side. Well, this is the atmospheric pressure, so you don't have to worry about that, so that goes away. So then you don't even have to worry about the G's, because those are going to be the same, okay? So the whole key to this is that it isn't the 10.2 centimeters. It's the height that's above this point. So those were 3 points, and if you did it right, you used this centimeters, only took off 1. But what you have to use is that you have to use this depth here, which is like 17 centimeters. So, because this whole thing from here to here is 27.2, this is 10.2, that means this is going to be 17 centimeters. So it's this 17 centimeters here that has to go in there for the height, because that's what's going to determine that pressure. It isn't the empty space above it, it's right there. Then on that next question, it was a rocket is continuously fired. Okay, so here's your rocket. Okay, we're going to fire this up. So, well, if you look at UG equaling mgh, so clearly the gravitational potential energy is going to be increasing as this thing goes up. Okay, so we're going to see an increase in UG. It's starting at rest, and it's going to be going faster. So kinetic energy is 1/2 mv squared. So your kinetic energy is going to get greater. And then the last column over there, I think this is what I think some of you got confused on, where I talked about system mechanical energy. And with system mechanical energy, that's just the sum of the whole thing. So you're increasing your kinetic energy, you're increasing your gravitational potential energy, so the overall energy of the system is increasing because of the fact that you're firing this rocket. Now, in contrast to that, if I were to just toss this up in the air, okay, now here's the difference. If I were to just toss this up in the air, then yes, my kinetic energy would be decreasing, and my gravitational potential energy would be increasing. And those two values are going to add up to whatever that constant is. But what's different with this one is that you're firing a rocket engine, okay? So you're not slowing down as you go up. You're going faster and faster and faster, and that's what you had to see. So usually if you missed it, you put B, because you said increasing, then the system mechanical energy is constant. That would be true if you threw it up in the air, but since you're firing that engine, everything is increasing. So 7 should be A. The question on number 10, where you had the cylinder and it was rolling down the hill, okay? So here's what you have to realize on this one, is that UG at the top, because it's rolling down, is going to equal the kinetic energy and the rotational energy. Those two values have to add up equal to UG. Now, if it just drops off the back, hey, UG equals KT. But since it's rolling, it's splitting between those two values. So you have to go mgh equals 1/2 mv squared plus 1/2 I omega squared, and that's where you've got to use the 1/2 mr squared, and then the v squared over r squared, and then your r squared cancels out. Your masses all drop out, so you get GH equals 3/4 V squared. So V equals the square root of 4/3 GH. So then you find your velocity and then you plug that back in. On number 11, this is the question with Bubba. He's on top of this and he's going to shoot this out like this, okay? So some of you went through a god-awful amount of work to find the time. And some of you forgot that what happens in the x stays in the x and what happens in the y stays in the y. So the easiest way to find the time is go, oh, x equals 1/2 at squared plus v naught time. Well, you don't have any initial vertical velocity, so this drops out. So then you just go, oh, 2x over a, the square root of that is going to equal time. Okay? So you're going to figure out how long it's in the air, which works out to be 1.28 seconds. And then you've got to use that area 1, velocity 1 equals area 2, velocity 2 to figure out how fast it's going when it launches. And if you do that, that new velocity is 0.667 meters per second. Multiply that by how long it's in the air, boom, you get like 0.853 meters. Okay. Those were the two that were kind of missed the most. That question, it's question number 25, unless you have your test, but it's the question about a sealed container of air has been sitting on a table in a dark room for a very long time. The room is always kept at a constant temperature. Which of the following best describes what will happen to the speeds and average kinetic energy of the molecules of the air in the container? Now, remember, the whole key to this is that you're talking about average kinetic energy. So if you look at a system of particles, whether that's Timmy in a classroom or whatever, these particles are always bouncing around. Okay, this is what creates pressure. If all the oxygen and nitrogen molecules in my room decided to say, screw it, we're not going to move around. We're just going to chill out. We're going to have a strike. And all these particles settled on to the floor. I would walk into this room and I would walk into a vacuum and it would be bad. So there's 1,000 things that I worry about when I walk into this room. One of them is it not being a vacuum, okay? Because I know these particles are always moving around. So what's going to happen is that they're going to hit, they're going to bounce off, they're going to run into each other. So they're always changing speeds, okay? They're always changing speeds. So, they don't have that on here. They used to have an average equation. Never mind. I was going to point out an equation that used to be on here, but there's not. But here's the whole point, is that when you warm something up, on average, you're making these particles move faster, but at any given point, you have some moving slower, you have some moving faster, you have some hitting and changing directions. So this is why on 25 that answer is B. It says some molecules will speed up and others will slow down, keeping the average kinetic energy of the molecules constant. So that, you have to remember what creates average kinetic energy. And then on that question 26, it's got this system going across like this, okay? So here's the whole point on this one, is that this is going to start with some initial temperature. That's going to end up at some final temperature, no matter the path. So you're going to have the exact same change in temperature. Well, delta U equals 3/2 nR delta T. So since it's going to have the same change in temperature, it's going to have the same change in internal energy, which is what delta U is. So then, delta U also equals Q plus W. Well, this one has a smaller work, but it's going to have a larger value of Q. The upper system has a larger value of work, so it's going to have a smaller value of Q. So that's why on 26, your two correct answers are, it says which of the following would be the same: the change in internal energy and the temperature of the gas at the end of the process. The thermal energy transferred isn't the same because of the fact that you're going to have a different value of Q. The work isn't going to be the same because the areas are different. Other than that, the test went pretty well. Your scores are input into the grade book. I'm going to make another video for the review for the final, which I will dump out in just a second.